Hi, we are going to discuss limits that fail to exist. In general, there are three types of behaviors that you recognize when limits fail to exist. The first one is probably what you already know by now, is when one-sided limits are both finite but they are not going to equal each other. Let's take a look at example 1. It's a graphical one, so the graph of f of x is here. If we try to find the limit as x approaches -1, because we're trying to find the limit as x approaches -1 from the left of f of x. So on the left it's going to be here and it's going to approach 1, but the limit as x approaches -1 from the right of f of x, so we're approaching from this side, and this approaches a value of -2. So these two are not going to equal each other, even though they're both finite. So here the answer is going to be the limit does not exist. Okay. This example, now we have a piecewise function given to us. So what we need to do is evaluate each one-sided limit. We're trying to find the limit as x approaches 1. If we do the limit as x approaches 1 from the left of g of x, we're going to substitute into the first function because that's where you have values less of 1 for x, which is going to be direct substitution, 2 times 1 squared minus 3, and it's going to be -1. When we're trying to find the limit as x approaches 1 from the right of g of x, we have 2 times 1 minus 1, and that answer is 1. Again, they don't equal each other, so then therefore the limit as x approaches 1 of g of x does not exist. Okay. There are some other situations that you need to know. When trying to find the limit of the absolute value of x over x as x approaches 0, if you think about how it works, the function absolute value of x can be written as a piecewise function. What do we know about absolute values? It's going to equal x when the value of x is 0 or positive, and it's going to be the opposite of x when you have a negative value of x. So then what happens with absolute value of x divided by x? Well, first of all, we should know that 0 is undefined. Well, when you substitute 0, you get 0 divided by 0. We know it's called indeterminate form, and there is a possibility of having limit there. But we cannot use 0 as a value for this expression because you're going to have to divide by 0. So when we apply this here, what we're going to get is we're going to get 1 when x is greater than 0. Note, I'm excluding 0 now because I cannot use it. And negative x divided by x is going to give you -1 as x is less than 0. Now, the fact that 0 is not a value we can use does not really impact the limit. That's not necessarily the case, but so what happens then? When you try to find the limit as x approaches 0 from the left of the absolute value of x over x, you are going to the left, you're going to get the left of 0, you are going to get -1. And then as x approaches 0 from the right of the absolute value of x over x, that's here, and the value is 1. They don't equal each other, this limit does not exist. I'm just going to write D and E to save some time. A similar problem here. So we have the absolute value of x minus 4. What do you know about that? The absolute value of x minus 4 is going to be x minus 4 if you make the value of x greater than or equal to 4, right? What happens when it's less than 4? It's going to be the opposite of x minus 4 when x is less than 4. And then when you write 4 now I want to note that 4 minus x is the opposite of x minus 4, so let me write that as negative x minus 4 divided by x minus 4 absolute value. So that's going to be you dividing this quantity by this. So when you divide negative x minus 4 by x minus 4, that's going to give you negative 1. That's when x is greater than 4. Again, I have to get rid of 4 because I can't use it anymore. When you divide negative x minus 4 by negative x minus 4, which is going to replace that, I'm going to get positive 1 when x is greater than 4. So you can see that one-sided limits are not going to equal again, because this is the left-hand limit is going to equal, hold on, I made a mistake, I put them both in the same direction. Left-hand limit here is going to equal 1, and the right-hand limit is going to equal negative 1, hence this limit does not exist. So that's one situation when limits fail to exist, when one-sided limits are finite but do not equal each other. The second possibility is the function increases or decreases without bound. That's when one or both one-sided limits are going to be infinite. Let's take a look at this example. So what we have here is this piecewise function, and so this is the graph of f of x. And what I'm trying to do here is figure out the limit at 2. So what do we have at 2? If I look at the limit as x approaches 2 from the left of f of x, I'm going to negative infinity. This is actually already enough for you to conclude that this limit fails to exist. But just to make the point about the whole process, and when you have the right-hand limit, you're approaching from the right, you're approaching 1. Well, you can't really talk about them not equaling each other because one of them is infinite. But the important thing here is this part, that it's something that is infinite, we have unbounded behavior, and therefore this limit fails to exist, and our limit does not exist. Here's example 6. So we have this function 5 over x minus 3. We know it doesn't exist at 3. If you're going to try to look at the limit as x approaches 3 from the left, so this is how we analyze that. If you approach 3 from the left using numbers slightly less than 3, if you use numbers slightly less than 3 in x minus 3, this expression is going to be negative, but this expression is going to approach 0. When you a number is going to be very, very close to 0, you divide 5, well, any number by a number very close to 0, you're going to get infinity. Well, either positive or negative. Because we're approaching 3 from the left, we're going to get negative infinity here. And when you do the same thing from the right of 3, you are going to get, using the same logic, think you're going to put a number slightly greater than 3 here, you're going to get a positive number on the bottom. So it's positive infinity, but this limit still fails to exist. A couple more. The previous problem, they were heading towards, one was going towards negative infinity, the other one's going towards positive infinity. This here, x approaches negative 1, the denominator, if I use direct substitution, is going to give me 0. The limit as x approaches negative 1 from the right of 2 over x minus 1, x plus 1 squared. We're using numbers slightly less than negative 1. You are actually going to get a number that's going to be positive here. Well, actually, yeah, no, I'm sorry, I'm doing the right-hand limit. Okay, so the right-hand side of negative 1, number slightly greater than negative 1. So in here, it's going to be positive. But you're squaring it anyway, so it's going to be positive regardless. This is going to give you positive infinity. When I look at the left-hand limit, that's going to give me still positive infinity. But the fact that they both go to positive infinity, and actually they're going to go to positive infinity at the same rate, is irrelevant because they're both unbounded, and the limit does not exist. This piecewise function, we're going to take a look at one-sided limits. So we're approaching 1 from the right, let's start from the left of g of x. So on the left, we're going to use the first function. So we're going to plug it in here. We have a number slightly less than 1. Slightly less than 1 minus 1 is going to give you a number very close to 0. Negative number, you square that, becomes positive. So 1 divided by something very close to 0 positive is going to give you positive infinity. The limit as x approaches 1 from the right of g of x. Now we're using the second equation. And in here direct substitution works. It's 2 over 1 plus 1, which is 1. Again, one of our limits is infinite, and therefore this limit here fails to exist. All right. The last example that I have, it's a classical textbook example, this function. If you try to figure out the limit of sine of 1 over x as x approaches 0, well, first of all, we know that when you plug in 0, 1 over x is going to be indeterminate, but that never stopped us from at least attempting to find limits. So what is going to be different here? The issue with this function is as x goes to 0, 1 over x goes to infinity, whether you're coming from the left or from the right. And the farther you go with x, the faster the function sine of 1 over x, the closer you get to 0, the faster the expression sine of 1 over x is beginning to oscillate. And what happens here, if you actually graph this function using some kind of a dynamic graphing tool like Desmos or GeoGebra, and you're going to try to zoom in, you will see that the more you zoom in, the darker it's going to get, which means the rate of oscillations is going to increase very rapidly, and this limit does not exist. Okay, so there is a way to prove it, but we're not going to get into that. This is just something that you need to know, and that's how it is. Okay, so I hope this helps.